Well, thank you again for being here. So I will be presenting the project LEAP-HCS, which stands for Leveraging Differentiable Programming and Online Learning for the Design of Hybrid Climate Simulators. So the overview of this presentation will be as follows. I will start with a general context and motivation with a main focus on maybe current limitations in climate models due to parameterizations. I will then give a little bit of an introduction into how we are planning to try to tackle this climate model tuning problem using ideas from what we call here online learning and differentiable programming. I will then go through a detailed description of the project with specific or detailed description of each work package, what they intend to do, and with some perspective on recruitment. And at the end, I will end with some administrative aspects regarding governance and timeline. So in an Earth system models, the different components of the Earth system, whether it's the ocean, the atmosphere, or the land components, are represented using a discrete numerical representation in our computers that try to kind of mimic or try to approximate the underlying physical, chemical, or biological processes. So in practice, each of these components is represented or is discretized spatially, and is propagated forward using by solving a set of equations. So, for example, in an atmospheric component of a climate model, the state of the system that is represented here as UT can be seen as a collection of some environmental variables, so things like temperature, wind speed, or humidity at each of these grid locations. And the time stepping function or the time evolution function represented here as psi is derived from laws of thermodynamics and fluid dynamics. Now, each of these components is not run independently or in isolation from each other. They actually do share information with each other in the form of fluxes of things like heat, momentum, carbon, and fresh water, for example. And this is used to build a coupled climate model that actually try to mimic the interaction that structure the actual climate system. Building and running, there are lots of challenges in building and running a climate model, and most of those challenges are still active research fields. And those include the development of numerical methods with continuous progress in space and time discretizations. There are also lots of challenges regarding high performance computing aspects, with strong emphasis on making climate models faster and less energy consuming. There is also lots of progress regarding model validation, with continuous progress in past and current iterations of the coupled model intercomparison project, for example. And there is also lots of questions or lots of work regarding uncertainty quantification of climate models, mainly uncertainty quantification of future climate projections. Now, when talking about uncertainty quantification, most of the uncertainty that is here in climate models is due to the fact that we are representing a continuous system. So here our climate on using a discrete representation in our computers. So this means that all of the small scale processes or all of the things that happen inside of a grid cell cannot be represented. And since our system, the climate system, is a multi-scale system, all of these small scale processes will have a strong impact on future climate evolution and changes. So examples of those small scale processes include, for example, in atmosphere models, things like convection and small scale clouds that cannot be represented in atmospheric components of climate models. And subgrid scale processes in ocean models might include things like small mesoscale and submesoscale eddies that are too small to be represented on ocean grid. And there are also other processes, so for example, vertical mixing that is not explicitly resolved by the equations. Now, in practice, all of those processes, small-scale processes, are represented in climate model by using some kind of semi-empirical laws that are derived from physical principles. They are called parameterizations. And those parameterizations actually depend on some unknown parameters that we need to tune in order for the climate model to represent at least historical observations. Now, in most of the climate modeling centers, the tuning of these parameterizations is manual, and we believe that there are some issues with tuning manually climate models. So, for instance, it increases model development life cycles, and sometimes it can induce uncertainty in climate simulations, typically when the tuning fails to reproduce historical observations. So based on these observations, the goal of LEAP-HCS is to derive automated tuning methods for parameterizations of climate models by using ideas from online learning and differentiable programming. And not only that, but we also aim to evaluate the potential of augmenting current state-of-the-art parameterizations. So typically things that will be discussed by Julien in his keynote, by adding deep learning components into these parameterizations and training them in order to make the climate model simulations reproduce faithfully observations. And maybe one of the most important objectives of this project is to make sure that the tools that we actually develop are going to get used, are designed, sorry, for to be used on climate model components. With some demonstrations that are directly targeting ocean component of climate models. So I will now give a little bit of an introduction into how we are planning to do this or how we are planning to solve this climate tuning problem, or at least try to do it using ideas from what we call here online learning and differentiable programming. So as we discussed in the introduction, a climate model can be seen as a function psi that takes as an input the state of the climate at a certain time ut and output this state at some future time. And as we also discussed, this psi is dependent on some set of parameters that we need to tune in order for the climate model to represent our true climate. Now, if we think of this parameterization or parameter tuning problem from the viewpoint of a climate modeling, typically when we have some physical parameterizations with a couple of parameters that we want to tune, and besides manual tuning, which is actually the state of the art in most of the climate modeling centers, there are some recent state-of-the-art methodologies that are starting to emerge and that actually can be used in order to tune parameters of climate models. And this include things like history matching or gradient-free optimization methods, so for example, ensemble-Kalman inversion techniques. Now, we do not want to use this because the issue with these kind of methods is that they do not scale very well into high-dimensional parameter spaces, which is typically the case with deep learning models. And since we want to at least evaluate the interest of augmenting physical parameterizations with deep learning, we decided to work with gradient-based optimization techniques because they are state-of-the-art in at least optimizing deep learning models. And they can also be used in order to tune free parameters of physical parameterization, so they can provide some kind of a unification in tuning both physical and learning-based parameterizations of climate models. So we want to do gradient-based optimization. Now, second step is we need to define some kind of an objective or a cost function. And one particular cost function, this is what we call online learning. There are other ones, we can discuss about it, but we will be working with this kind of cost functions, and we'll be discussing why later on in the presentation. So one particular cost function can be constructed as follows. So we start from initial condition ut, and this initial condition can come from either a reanalysis data set, for example, or from some high resolution simulation. We then propagate our initial condition using our numerical model forward. We compute some observable, and then we compare this to some ground truth observations. And this again can be, for example, observations, reanalysis, things like that, or high resolution simulation. We compute a cost function based on this ground truth, and our optimal parameters will be the minimizers of this cost function. Now, as I said, we want to do gradient-based optimization, so we need to compute gradients. And when we try to compute gradients of this kind of cost function, we can show that it can be decomposed as a gradient of a regularization term, if any. It's not really important, plus something that, this is the most important part, plus something that will depend on the gradient of the numerical model. And this is an issue because for most of the climate models and climate model components that we truly care about, we do not have access to this term here. So we need to figure out a trick or a way in order to either specify or to approximate this term in order to solve the optimization problem using gradient descent, for example. So now if we assume that somehow we can get access to this gradient, it's not the case for most of the climate models that or climate model components that we care about, but let's just assume that we can do it. Google Research showed in their neural DCM paper that solving online learning problems can lead to having numerical models that achieve both good short-term forecasting performances as well as long-term reproduction of at least the climatological behavior of the observations. And this is important because it shows that this kind of methodology, solving this kind of online learning problem, can allow to tune parameters of climate models. Now, what we want to do is that, maybe this is important also, but in order to do this, so Google Research had to rewrite an entire numerical model, an atmospheric numerical model in JAX, which is a programming language that allows automatic differentiation in order to compute this term, this gradient term. So obviously we cannot do it for all of the climate models that we truly care about. It's too expensive. It will take too much time in order to make the community converge towards a tool like this one. So we cannot, this is not a solution that we can have, at least in the time span of a project that will be 4 years. So what we propose in LEAP-HCS instead is to design gradient-based optimization methods that would allow to solve online learning problems, so pretty much similar to what neural GCM did, but with some extra challenges that we need to care about because we are working on actual climate models and actual climate model components. And those challenges are the fact that we need to think about how to interface the numerical model that we want to work on that lives in low abstraction, very stable programming languages and that run on CPUs, potentially with some object that lives in very high abstraction languages that run on GPUs, and we need to do this interface not only at inference time, but also at training time. So we need to think about how to do this. Second problem, obviously, is what I described earlier, is the fact that we need to, if we want to solve this gradient-based optimization using, for example, gradient descent, we need to, we do not know how to compute this term in practice, so we need to figure out a way in order to either specify or to approximate this term in order to solve the optimization. Now, we can kind of divide the main goal of LEAP-HCS into 3 main objectives. So the first one is we need to do a validation of online learning-based methods on numerical models that use differentiable programming for state and parameter calibration, because we saw in neural GCM that it works, but it works on a particular setup of an AI-based parameterization. So we need to see whether online learning can be useful to tune actual parameters of physical parameterizations. Second objective is we need also to develop and validate, as I said, gradient-based optimization method that take into account the lack of differentiable programming capabilities of current climate models and current climate model components. And maybe a third objective, maybe it's one of the most important ones, is the fact that we need to target the first 2 objectives in the optic of having demonstrations that are going to be built on actual ocean models of climate, ocean model components of climate models, with targeting applications that include parameter calibration and spin-up acceleration. Now, I will go into maybe a more detailed description of the project. This includes a detailed description of each work package, what they intend to do, and also with some perspectives on the recruitments. So we'll start by having maybe a little bit of an overview of each work package and how they feed into each other using this figure, and then we'll go into the details of each work package. So in this figure, we have this figure represents how, for example, an ocean model is used today. So we start from an initial condition. We feed this an initial condition into an ocean model, and it's a combination of a dynamical core plus some parameterizations with here the parameters that we want to tune. We run this ocean model for a certain amount of time. We then compute an observable out of this ocean model. For example, here it's the amok strength for different water levels. And then we compare the simulation to some actual observations of these observables. And we tune, what is usually done is that we tune, usually by hand, the parameters of the submodels of the parameterizations in order to be able to reproduce the observations. Now, what we propose to do in LEAP-HCS is, instead of doing this manually, is to use the observations in order to construct a cost function and then compute or optimize this function using gradient-based optimization. Now, as we discussed earlier, there is an issue with this term. We do not know how to compute the gradient of our numerical model. So we'll structure our project in order to maybe build methodologies in order to be able to approximate this term so that we can solve the optimization problem for actual climate model components. So work package number 1, we will be developing a fully differentiable ocean model benchmark. And the goal of, maybe I'm a little bit contradicting myself, because I'm saying that we need to design optimization method that take into account the fact that we cannot differentiate, but the work package 1 is all about differentiation. And the goal here is to actually have a control environment in which we can evaluate. It's actually 2 objectives. The first one is the fact that we need to have a control environment in which we can evaluate whether solving online learning problem might allow or not to tune parameters of ocean models when having the exact gradients. So this is the goal number 1 of this work package. Work package number 2 is to use this fully differentiable ocean model, in order to design gradient approximations that on problems at scale that later on can be used, for example, on NEMO. So this is the goal of work package number 1. And once we develop this fully differentiable ocean modeling benchmark, we will be using it in work package number 2 in order to derive online learning strategies for actual numerical model that lack differentiable programming capabilities. And the algorithms that will be outputted from this work package will be used in work package number 3 and work package number 4 on NEMO for doing NEMO tuning of NEMO parameterizations, and also for spin-up acceleration of the ocean model. Now, I will go a little bit more into the details of the first work package on the fully differentiable ocean modeling benchmark. So we actually achieved quite the progress in this work package, because we are not building an ocean model from scratch. It will be it will take too much time and it will be too expensive. We are using the maybe before talking about what we are using, I will talk about the different tasks of the work package. So as I said, in this work package, the goal is to develop a fully differentiable ocean modeling benchmark in order to develop and validate optimization methods that can be used on actual climate model components. And it can be we separated the work in this work package into 3 main tasks. So the first task will be the implementation of fully differentiable 1-degree global ocean model. Second task is to build a realistic 1-degree global configuration, so with the correct forcings and the realistic bathymetry, things like that. And task number 3 is to design an online learning experiment on this realistic 1-degree global configuration. So here will be maybe some technical choices about the training observables, the reanalysis, or the climatology dataset that will be used in order to do the training. It's basically building the online experiment, the online learning experiment on its own. So as I said, we kind of achieved quite the progress in this first work package. As I said, we are not building one from scratch. We are using the versatile ocean simulator, which is developed and maintained by Team Ocean in the NBI in the University of Copenhagen. It's the ocean model that is written in pure Python. It also has runs in GPUs and has a JAX backend. So we worked a little bit on the JAX backend in order to be able to compute gradients of the numerical simulation by using automatic differentiation. So this is now possible. We published the work about this recently. We also had some initial experiments that do both parameter calibration and bias correction of ocean model using a deep learning model. So in the first row, what we did actually was to have a kind of an idealized simulation in which we perturbed a little bit the value of the parameters, and we tuned those parameters using online learning. So it's kind of an example of tuning, of doing online learning to tune physical parameterizations with a small number of parameters. Here it was two. It was bottom friction and horizontal viscosity coefficient. And the second experiment in the bottom row was on actually training a deep learning model in order to bias correct the ocean model. So we show that with online learning it works very well. So we want to design the same kind of experiment on a global ocean configuration. This is tasks 2 and tasks 3 of this work package. So what is interesting is that these two tasks are in relationship with another project called NeuralGCM, which is granted in the context of the AI action of the PPA Océan et Climat. And the goal of this other project is to build a hybrid model that reproduces the GLORIS reanalysis. So what is interesting here is that LEAP-HCS will benefit from some extra human resources time and also from collaborations in the context of this project. And regarding the recruitment, we are expecting to, and we'll go back a little bit on maybe more on the details of this, but projecting to recruit one research engineer to work from month 0 to month 12 on these 3 tasks, so on the entire work package. Now, the global ocean, the fully differentiable global ocean configuration of the work package number 1 will be fed into work package number 2 to design gradient approximations that allows us to solve the online learning problem with taking into account the fact that we cannot differentiate the numerical models. And so this work package is mainly decomposed into 2 main tasks depending on the length of the control window represented here by an arrow. So the first task will be to evaluate low-order gradient approximations that we developed in some of our research works on problems at scale. And the goal here is to evaluate whether parameterizations trained to or calibrated in a way so that it controls short-term control windows can be able to reproduce a good long-term simulation, typically in climate timescales. And in task number 2, the goal here is to maybe target more medium-range control windows by designing gradient approximations that allow to optimize these kind of cost functions, but for not short-term control windows. And for this work package, we are currently in the process of recruiting one Master's 2 internship that would lead to the PhD. So it's online, so if somebody knows a motivated student, so please reach out to me. And maybe the final 2 work packages, the applicative ones on NEMO, will be the use of the gradient approximation methods to solve parameter tuning and spin-up acceleration of the NEMO ocean model. And this work package will be in collaboration with the TRACCS Compact PC5, because we'll be using the NEMO tool that is currently in development, and we'll be hearing a little bit from it by Alexis in his presentation. And so the 2 work packages will focus on so WP number 3 will focus on tuning parameterizations of NEMO, and we'll focus on the vertical mixing and eddy parameterizations. And WP4 will be focusing on spin-up acceleration. There will be some maybe methodological work to be done in WP4 in order to formulate spin-up spin-up acceleration as a solution to non-optimal control problems, typically a strong constrained 4D VAR problem. With a second task that is going to be more applicative about finding optimal initial condition that would lead to a small spin-up of the ocean models. So for these two work packages, we are expecting to recruit two human resources. So a PhD student who start from month 12 to month 48, and a postdoc that starts at month 12 also, but that works for, it's an 18-month postdoc. He's going to work on work package number 4. Now I will go through some practical aspects regarding governance, timelines, and recruitments. So sorry for the busy timeline. I will not talk too much about it because I think that I specified all of the recruitments that we will have. We'll have actually a human resources per work package, so it's easy. But what I would say that we are somewhere here into the project because the project started officially in November. So we are in the process of recruiting the PhD student that will work in this blue areas, the work package number 2. And it might look like that we are late in recruiting the research engineer, but not the fact, because we, as I said, we did quite the progress in work package number 1. So we are planning to shift the recruitment of the research engineer toward month 6. Maybe some administrative aspect. The coordination is led by a single PI, and it's a mono-institution project at IMT-Atlantique. We are planning to have yearly progress meetings with project externally advisors, external board that we validated after some discussion with the reviews from the funding process. And regarding the research ecosystem, there are close collaborations, as I said, specifically in WP number 3 and WP number 4 with the TRACCS PC5, and there are lots of synergies with PPA Océan et Climat, as I said, regarding the development of the global ocean configuration, the 1-degree global ocean configuration that is related to this project. And also with there are also lots of synergies with some chairs, local chairs that we have at Brest, specifically chairs AI for Extreme, hybrid regional ocean models, and European project AI for PEX. We'll now conclude by saying that LEAP-HCS bridges the gap between new AI frameworks, so things like languages that allow for automatic differentiation, such as JAX, and new models that are written in Python, such as Veros, and current climate model components, NEMO. And the impact of the project targets to derive automated calibration methods for the climate modeling community. So that's all for me. Thank you very much. And I think I have maybe 2 minutes for question, even if we do have a discussion session after the presentations. Thank you. One question, maybe?
Yeah, well, so you mentioned all this connection with the ocean models to use the application targeting in this work. How would this work apply for atmospherical and surfaces components, or maybe atmosphere because it moves just like the ocean?
Okay, so yeah, in atmosphere, I think conceptually the transfer should be easier when compared to other climate model components, but maybe the only break or frein that we see into a direct application is to have maybe similar tools in the atmosphere than the ones that are currently being developed for the ocean. Meaning that for the ocean, there are efforts in TRACCS PC5 in building this NEMO Python coupler that we can use at training time. So if we have something similar for the atmosphere, then the application is direct. Thank you.
Well, thanks for the presentation. You mentioned the dinosaur framework.
Yeah.
I'm not sure I quite understood like how this framework is load and what you intend to solve with the current project.
Dinosaur was only may be presented as a motivation about, so if we have atmospheric models such as dinosaur that are fully differentiable, I mean, would directly do gradient-based optimization in order to solve the online learning problem. There is no LEAP-HCS project, basically. So LEAP-HCS, the goal here is to do the same thing, but on numerical models that do not support automatic differentiation.
Oh, okay, because dinosaur is something completely new, right?
It's written in JACCS. Basically, you can just compute gradients using automatic differentiation, whether on Nemo, for example, it's on Fortran, you do not have access to. You cannot backpropagate to compute, to do gradient descent, basically. Okay. So you need to figure out a way in order to do it on this kind of. Okay, so I think I will stop here because we now have a keynote presentation by Julien Mac, who is with us online.
All right, thank you for your time. So I hope the internet stays stable. I'm actually in Japan at the moment. I'm using hotel Wi-Fi, but it probably should be okay. So my name's Julian Mack. I'm currently a faculty member at Hong Kong. I also have an honorary position at the UK National Oceanography Centre. So I've been a NEMO user and developer for the past, since about 2017, and currently sit as one of the co-chairs of the eddy parameterization working group in NEMO. So I've been asked to maybe provide an overview on eddy parameterization in NEMO, at least how I kind of see maybe some of the machine learning type approaches be useful for NEMO. So I would just caveat this is going to be a very biased overview. So naturally, I would just say that I'm a machine learning skeptic. I use a lot of machine learning, but I'm somewhat skeptical of the kind of things that can and cannot work with machine learning. The kind of things I'm going to be talking about are largely biased towards the ones that I think would actually work, which is different to, I would say, most of the things that are actually available currently. So I would also just say it's very interesting to see the outline of this project, because I think we were talking about whether we do try and do similar things in a slightly different context in Oceananigans, which is a model written in Julia, which has full differentiation. I think that was related to one of the questions before a slightly different problem. So it is true NEMO currently does not allow for, because it's written in Fortran and it's not, it doesn't have backpropagation capabilities to do the online learning. We had this conversation in NEMO, I think maybe last October or September time, whether we would in fact rewrite NEMO to have full differentiability. That is a question that's been discussed, and I think that's not in fact happening. At least there's no real consensus on whether we should actually do this. So for the meantime, this is not going to happen. So we're still going to try and rely on approximating methods that Said is talking about. All right, so I'm just going to do a quick overview on things. I think this is not entirely new, but I think Said's already talked about most of this. So in ocean modeling and generally modeling of, I guess atmosphere, ocean, generally anything which is a continuum of sorts, there are things which are different processes and features which are multi-scale. So the kind of things we might be interested in are the climate change and the large-scale circulation, which are large spatial scale and long time scales. But then these coexist with, in principle, these coexist with small scale fluctuations on the sort of smaller space scales, but also shorter time scales. And given this is essentially a multi-scale problem. Anything in the large scale affects the small scale, and all the things at the small scale affects the large scale. So if you were to quote unquote do things properly, then in order to simulate climate change in large scale circulation, if you want to do what would be called direct numerical simulation, then you need to resolve down to the hourly and possibly seconds timescale and at the centimeter scale. Computationally, that's extremely expensive to do. So that's not what we do. In practice, what we do is we have a limitation. When we do reports, then we have to say this needs to be. If you want to do, like a 100-year prediction, and it takes you 1,000 years to do that, then that's not very useful. So in reality, what you do is given the computation resources, you choose the time scale or choose the space scale. And then you live with the fact that you haven't resolved the things which are below the scale, below the grid scale. So that would be what's called parameterization, essentially. So this would be one output from NEMO at the 12 degree, 1/4 degree, and 1 degree. So these are the default resolutions at a global in a global ocean circulation at the moment. 12 degree would be what's called mesoscale eddy rich or eddy resolving. So it's eddy resolving except at very high latitudes and in very shallow regions. On the other hand, you have the 1 degree, which is effectively what's been used in the past IPCC reports and probably the upcoming one as well. And a 1/4 degree is some kind of weird regime in between where you kind of solve it, but then you don't resolve it properly. So given that the climate model is a ocean model, in this case multi-scale, and in the 1 degree you do not resolve the mesoscale eddies, but you also know that the mesoscale eddies feed back onto the large-scale state or the model climate, then somehow you want to write the effects back in. You have to somehow find some representation of these missing small-scale effects on the large scale. So this would be what I would call parameterization, or what we're talking about in terms of parameterizations. So all the things I said are not kind of limited to NEMO itself. Is generically any sort of multi-scale system has that kind of problem. One specific one of these is NEMO. So I don't think I need to mention too much about NEMO. So NEMO, even though it's got the title European in it, I would say France takes the lead, or takes a kind of majority of the lead in terms of the support and the human resources in the NEMO development and maintenance. So, for example, you've got the TRACCS program, which is of which NEMO is one part of. I think PC7 is one of the is the ocean component and the ice component. So you get consortium kind of support and people support for this because NEMO participates, at least as an ocean model, in multiple Earth system models, which inform the CMIP exercise, and these are then used for the to inform the IPCC reports, which end up informing kind of impact and policy essentially. So my point here is that the fact that so most of the skill in the modeled ocean ultimately depend on the parameterizations. So if you on fixing parameterizations, then you can improve the ocean model response or the simulated variability, etc. And these would end up having impacts at the policy level through these kind of CMIP exercises. All right. So it's fairly well known. So the problem, of course, then is that it's fairly well known these ocean models depend somewhat on the parameterizations, and they can depend on it fairly sensitively. So there's importance in how you constrain the uncertainties in the structure of the parameterizations, and also uncertainty in the parameters, the kind of extra tuning variables, which Said mentioned. So two examples I'm going to give you is so the first one is mixed layer turbulence. So this is so mixed layer turbulence is somewhat important in the ocean because this essentially gives you the mixed layer you can think of as the skin of the ocean. So it mediates the transfer between the atmosphere and the ocean. So these things are important for things like I guess the atmospheric variability, the ocean feedback. So Europe, for example, is warmer because the Atlantic is warm. The Gulf Stream is warm, so it's the Gulf Stream is bringing warm water up to the Western Europe. If you do not get the variability correct, if you do not get the representation correct, you might get biases in the simulated atmospheric response. In terms of carbon sequestration, you would want to make sure that you get the mixed layer turbulence because that affects the carbon intake into the ocean and then the subsequent transfer into the deeper oceans. So here what I'm showing is a figure from a colleague of mine, Li Qing. So here what they do is they compare a whole load of parameterizations for the mixed layer turbulence. So the same parameterization within different ocean models, and also different parameterization of the mixed layer turbulence, or the mixed layer turbulence. So you've got some reference, and the colors are essentially denoting bias. So you've got massive biases in this model and a negative bias in here. So we know that, for example, these ones are the same parameterizations but in different models, and these are different parameterizations. So there's the variability between the different parameterizations themselves, and then within the same the same parameterization but used in different models, these have different responses as well because of non-linearity. So some of these we know are related to the parameterization themselves. Some of these are nonlinear feedbacks of the model. There are things which generically no parameterization currently seems to get correctly. So there are things in the Southern Ocean which is particularly is a particular issue which has implications for things like anthropogenic carbon uptake in the ocean. Next one I've worked on, so this would be on changing the mesoscale eddy parameterization. So here the bottom one would be where you use a standard, what's called the standard Jack-Williams scheme. So we have some previous work in terms of theory and also some idealized model experiments where we think the use of this new one called geometric is a variant of the GM scheme, really. Gives you reduced sensitivity. So part of the point of this paper was showing that there is in fact a reduced sensitivity. So here you can see that the colors are lighter, which is indicating reduced sensitivity. This is ocean heat content. So this is really talking about the ability of the ocean to absorb the change in the excess heat or excess energy relating to global warming, essentially. The second thing we made a point in this paper is that we compared, there's a parametric uncertainty. So here one we find is that there is a thing relating to the dissipation of subgrid energy, and roughly 50% change is equivalent to, in certain climate metrics, is roughly equivalent to halving or doubling the wind in the Southern Ocean. So the point I want to make here is that we don't really think the ocean, the wind is going to change by 50% or by double or half under climate change scenarios. But we don't really have any idea what the dissipation should be. So this was indicating that you fix some problems, but then you introduce some sort of uncertainty, which well, at least it tells you where the problem is, but you still need to go ahead and fix this uncertainty in the parameters. Okay, so those are the two things I wanted to say. So let me just quickly go through and frame the parameterization problem in at least mathematically, or at least from a technical point of view, so I can talk about it and how machine learning might be useful for these kind of problems. So the way you normally do this is here I took a 12-degree model. So this is 12-degree Nemo actually in the Southern Ocean. So you see the Antarctic circumpolar current and you get these jets. So the idea of parameterization is you take a full field. So suppose you have some sort of full field, hypothetical full field. You define a grid box, which is your climate resolution. So here I took quite a big box, but you don't need to. And then you smooth it out. So by smoothing it out, you've essentially defined some sort of average, and you call this your climate state. And then what you do is you say the residual, this is your eddy field. So there is the eddy field which you want to somehow parameterize. So mathematically, what you have is you take your full field, you define an average of some description. You can think of it as an ensemble average, spatial average, temporal average. It kind of matters, but in practice, not really. So in practice, we take a spatial average. You probably should take an ensemble average for theoretical reasons. So you have the eddy part, and what you want is you know that you form the equation for the, so you can think of this as a climate state, and this is the variability, or climate and weather, if you like. So you know the average weather is going to give you some sort of impact on the climate. So when you form the equation for the climate, what you find is usually you've got some sort of statistics term, you've got a two-point correlation term you need to do something about. So this is the thing which is not resolved. So C here would be a resolved by the model. This is not. So somehow in a parameterization is you want to propose a form F, which takes your input, which is resolved, to give you something which is here, and this thing is going to be the thing that affects, so this F is now going to be the thing that affects your large-scale evolution. So that's basically what parameterization is. You just find this F. You can do this through expert opinion or as a data-driven or machine learning type problem, and you can represent F deterministically or stochastically. It doesn't really matter how you do this. So one example, let me just, given I talk about Jack-Williams scheme. So the Jack-Williams scheme would be an expert opinion deterministic type parameterization. So what you do is you take what's called the buoyancy field. So buoyancy would be related to temperature and salinity in the ocean. You take a diffusive light closure for this. So your uncertainty is now in the kappa, in this, your parametric uncertainty. So these kind of things, when you propose an expert functional form, you can start analyzing it. You kind of know what it can do and what it cannot do. So this one, we know it looks like diffusion is actually an advection. It's the skew part of the diffusive tensor. We know it mimics certain properties of baroclinic instabilities, and namely it flattens isopycnals. And we know that this is what baroclinic instability does. So these are widely used in GCM and ocean GCMs because there are many good things about it. One part is that these slumping isopycnals means you're reducing the available potential energy in the system. That has the added bonus of stabilizing your model. So this is good from a physics point of view and also is good from the numerics point of view. The introduction of the GM scheme reduced the law, essentially fixed the law problems with ocean models in the 90s. You had a lot of kind of spurious deep convection, so the ventilation was much larger than it should be. GM scheme is actually removes that. Okay, so as I've said, there are issues with this one. It's everything. When you do when you do modeling, you make a choice. So somehow there are good things and there are bad things with it. So here you can argue you're shifting the problem somewhere else, right? You're basically shifting the problem how you specify this kappa. So this would be parametric uncertainty. There's a structural uncertainty to say that, is this in fact the right form you should use? Because this one, so you can say this is doing something of the baroclinic instability. It's not doing everything, and it doesn't. So that's what I mean by structural uncertainty. Is this in fact the right function form that you should use? So that was a deterministic one. So here we have you can do this as a regression type problem as well. So if you can have a high resolution model, you diagnose this, and then you have you can diagnose this as well, and then just fit the two in some way. The first example, so for example, there's some work which was done led by Lausanne, led by Tom Bolton. So this would be when you represent the divergence of the flux. So this is an eddy forcing by a convolution neural network. You can do symbolic regression. So in symbolic regression, in principle, gives you some sort of interpretability. There's some recent work by Druth, which is looking at representing the flux instead by a multi-layer perceptron. And this is kind of in line with some of the work which was led by my PhD student, where we argue that you should probably you should do machine learning on the flux and not on the divergence of the flux for some kind of theoretical reasons. There are other kind of examples. I've only taken the ones that I happen to have access to. The things I would just kind of draw your attention to is that when you do machine learning, the first thing is that one of the things which is known, and this is an ongoing issue, is whether these parameterization or learned machine learning mappings, do they in fact represent or respect the underlying physical constraints? And are these numerically well behaved? So usually at least the things you get by default is that you get neither of those. They're usually violating some sort of conservation law, and they lead to model blowups. For reasons we kind of understand, actually. So it might be actually the fact that you're not respecting the constraints, which is leading to things not being numerically well behaved. All right. So the kind of things which are in NEMO is not really by kind of design. So partly one of the things you may want to know is that model developers tend to be somewhat conservative. So we want to make sure things don't break, or at least we don't regress too much backwards. So we tend to choose things, or at least there's a general consensus of choosing things that will lead to improvements. And most of these ones are, which are sufficiently informed. So by that construct, then most of the ones which are in NEMO are by design deterministic and also rely on expert opinion. It's deterministic because then your runs are reproducible somewhat. Rely on expert opinion because then the theoretical analysis tells you what the things do or cannot do, or at least the numerical experiments do. One of the practical reasons we don't have that many machine learning things is we don't have an interface. So I think that's what Alexis is going to be talking about. So there's a practical reason for that as well. And there's a whole load of things. So for mesoscale eddy parameterizations, which are normally diffusive based, the ones I worked on, which is called geometric, is really tackling the parametric uncertainty. There are things to do with grid scale type diffusion. This is kind of numerical, but also there's a bit of physics behind it. So the Smart-Gorinsky, for example, is a bit more physics behind it. There are things to do with wave-driven mixing, which affects the ventilation. So this normally affects what's called a dipycnal mixing. And then the things to do with mixed layer turbulence and other things like double diffusion and some mesoscales. So the thing I can tell you now is that the NEMO eddy working group, at least this year, we presented a work plan, and all of these are deterministic parameterizations in the eddy permitting regime. So this would be LEAP-QG, which is like Smagorinsky, but designed for rotating stratified turbulence. There's backscatter, which tackles one part of the mesoscale parameterization. That's not GM. So it's the extra fluxing of energy to large scales, which this is supposed to be targeting. Biharmonic GM is one approach on how you use this GM type scheme, but in the eddy permitting regime. So there are reasons why you should not use a GM when you have a eddy resolving, some sort of eddy permitting regime. It does some weird things to it. The energetic constraint as a neutral diffusion is like a variant of the geometric. Splitting is one of mine to deal with, is an alternative to doing biharmonic GM. So the kind of things we agreed on are the things that, again, because we're conservative, is the things that we know we can deliver. So it's not that we're not touching some mesoscales or we're not using machine learning approaches. It's just that in this year, these are not the ones which are in the priority. These are the 5 I've named are the ones which are in the priority for implementation point of view and testing point of view. Okay. So the way I see it, so this is going to start getting more biased because I use machine learning, but the thing I find there's a lot of hype with it. So I'm naturally, because I'm a conservative person. So I'm not denying the fact that I think machine learning is actually really powerful. Through the things like the universal approximation theorem and etc. And there's a lot of very powerful computing machinery which enables machine learning to happen. But it is also well documented that at least in the climate or the climate modeling or some sort of physical principle modeling, generally they don't satisfy the physical constraints, and the numerical models that result using the machine learning informed parameterizations tend to be quite fragile, possibly related to the fact they don't satisfy constraint. So you can imagine the case where you have a parameterization and is just adding extra energy into the system for no particular good reason. Then your model starts accumulating too much energy, then it breaks. So that has happened, and that's been reported before. There are ways to force constraints in, kind of better ways and in more, dubious ways. So there are ways where you force as a hard constraint. That's not a trivial task, and you need to design your architecture accordingly. So this would be, if you know these things, this is like forcing a constraint for what's called a Lagrange multiplier. You can do these normally within a joint. There are ways to force a soft constraint. So you force this by changing the definition of a loss function. So it's a bit like physics informed neural networks. These end up causing some numerical issues, but in practice, it would actually do stuff. It would do something, but it wouldn't necessarily do exactly what you want it to. So this is like an approximate conservation rather than a hard conservation. There are other ad hoc things to stabilize the model, sometimes stabilizing models, sometimes forcing constraint. Some of these are not entirely satisfactory. Enough of these are also very dubious. So this is, so there are people you can kind of see. One issue would be that you take a machine learning approach, you develop a parameterization, and then you put a stabilizer right at the end. Right? So then the machine learning is doing whatever it wants, but the stabilizer stabilizes it so well anyway. Then you say the machine learning thing works, but actually it might just be the fact that it's the stabilizer which is helping you. So that to me is that it's very hard to separate, and that's not very theoretically satisfactory, in my opinion. So one thing which is alluded here would be that you could also leverage the underlying model, and for this you need differentiable programming eventually. So with the online learning, but I think Said talked about this, so I don't really want to talk about it again. So one of the things I would just maybe say here is that so it's fitting to trajectories, and the idea here is that the control variables or things you adjust are the things within this N. So the N is a neural network or some sort of parameterization. So it could be a neural network as a parameterization, or it could be a neural network as to give you the parameter of the parameterization. So it's the thing that fixes the tuning, or the parameter somehow varies as a function of the state. And in order for this to happen, you need the model to be somewhat differentiable to do the full what's called a backpropagation for gradient descent type methods. But there's also approximate ways which Said talked about. In offline learning, you don't have that. In offline learning, you don't force a temporal correlation. So NEMO falls here. So NEMO doesn't have a adjoint. So there's no way to generate an adjoint to propagate information backwards. But that's not to say you cannot do this kind of online type, approximately online type learning. So I'm quite interested to see how this kind of the methods that are going to be proposed as part of this project. So the way at least I think about it is that when you include the model, that's one way you can kind of think of it as forcing and adding extra layer to the machine learning, say, to a neural network. So it is possibly one way to force a constraint which is inherent in the model, and in particular is actually forcing. I would like to think it's actually giving you some sort of correlation in the space and spatial temporal, the resulting spatial temporal correlations within the data. That's what we argued in the paper, paper led by a PhD student. So my personal bias is that I think the conservation part is very important for us, particularly for physics, because in this case, we know there are certain physical laws these things have to satisfy. So I would say current ML models do not, and the important thing is by default. So by default, they don't respect the underlying principles in the data. And there's no reason it should. What you would like is that the data comes out from the principles, and what you would like is to expose the data to the machine learning model. And the machine learning model, in learning the correlations, is also learning the conservation laws. That's what you would like. In practice, there's no reason it has to, and usually it doesn't by testing. Just from testing, it doesn't do that. And to me, it seems so. This is where this one. We're recording, so operation be too rude about this. So I get quite irate when I hear there are talks about how machine learning is going to replace everything. And most of the time, I guess I'm irate because I'm irate by it because they say machine learning things do better, but only in certain metrics. So if you dig a little bit more, then you can always make something that looks right, or at least sell something is improving in certain metric. But then if you look at other metrics, they don't. And that seems to be quite prevalent, at least in the things I see. And that's also the same thing when we talk about parameterizations. In parameterizations, you can say it improves the eddy kinetic energy signature or whatever. But if you end up killing the AMOC, or if you end up destroying the kind of things we care about, climate simulation, then that's kind of irrelevant. The fact that you improve the eddy kinetic energy if you do not have an AMOC. So some of these are not really presented holistically. So I think there is something to be said in by Said in deciding on the kind of benchmarks you need for judging whether something's improving things or not. In particular, it's like there was a lot of argument as to, we should only have numerical models or we should only have machine learning models, and there's no room in between. But in reality, you could have the two playing well together. And one way to do this is using differentiable programming. And there's no point reinventing the wheel. And particularly, there's no point getting rid of a very strong prior, which we have in the form of a numerical ocean model, in favor of a complete ML approach. And I think that's just not how I see it. This one I think I'm going to skip. So a lot of the arguments relating to who actually cares, because ML is going to introduce uncertainties, but there's so many uncertainties anyway. This reminds me of an argument relating to model numerical grids. So we now know that that doesn't, the numerical grid is very important. And also so to me, it's really about controlling the source of uncertainties. So you want to know, you can have unknowns, that's fine. If it's known unknowns, then you at least know which problem to tackle next. If it's an unknown, then that's a problem, right? You don't even know where to look. You don't even know where to dedicate your resources. That part I'm going to skip. So the kind of things I would like to see done, and it's also related to my personal agenda, I suppose. So this is going to be biased. So it's relating to what Said talked about, which is I think is your work package 3. So this would be, the main one I would like to see is using some sort of differentiable programming approach to be able to ingest high-resolution data or observational data as a way to constrain free parameters in parameterizations. So in particular, constraining the form of kappa or the three parameters that give you, so suppose you propose a form of kappa, then there would still be three parameters within there. So how do you specify those? So here what you're doing is you're doing expert opinion to restrict the kind of solution space you have, and then using a machine learning to target those things. The added benefit of doing that is you kind of know what these things do already. These are numerically stable and you know what they do. So if you vary the magnitude of these, then you only vary the magnitude of something, for example. It's not going to start artificially creating energy or whatever, unless you get negative kappas. So then it's doing known things in a slightly more refined way. So I think that's how I would see immediate impact would be essentially as a way to tune or constrain parameters. There are other things which is slightly next level would be, for example, one of the things that we are pushing for quite a lot is energetically constrained parameterizations. So that ends up shifting the problem on how you represent the ocean energetics. You could either do the same game again. You have a proposal for the energy budget, but there are three parameters in there. So try and fix those using high resolution data or observations, or using a kind of ML surrogate or a simulator for the energetics themselves. But again, then the problem is how do you constrain these appropriately? The thing I really would like to say, and this is, I think it's not just me, we would like to see interpretable parameterizations, and in this case, the kind of thing I had in mind was symbolic regression, but using online learning, right? So the previous example of symbolic regression in the ocean was done offline, and I think recently there were a few which was led by the Chicago group. So Pedram Hassan-Sadeh is involved in this, in the atmosphere. But those, I think, were done offline. So I would like to see how these things play, in fact, in the online approach. And the opinion is not just me. Maybe for a change, we can actually get machine learning models to tell us something new. One of the kind of gripes that I've been hearing from people is that, it does great, but is it actually teaching you anything new? And personally, I'm not very convinced at the moment. But maybe this is one possibility, because somehow you need the model to construct the evolution, or the kind of solution parameter space you can explore. One extra bit would be, I guess, relating to whether you can force statistical properties. So rather than having a deterministic one which has the right statistical properties, maybe it's better to just go straight for the statistics. Because we talk about climate emulation or climate simulation, and ultimately that's a statistical comment. So we want to target the statistics themselves instead. So to me, so I think I forgot what the word you use. I think it's climate simulation. So when I use emulation, I'm thinking of something slightly different. But ultimately, I think climate projection is influenced by the representational process. Therefore, it's affected by the parameterizations and also the free parameters in the parameterizations. If you're going to have emulators trained to do climate emulation, then if you're using the climate model output, then if those are flawed, then can you really say that much more about the climate emulation themselves? So to me, I think at least I would argue that a very important part in at least in the improvement of climate projection and possibly eventual climate emulation would be to improve or constrain the parameterizations, which help you to get slightly better behaved models or more accurate models, and also more accurate models, less uncertain models. And those are important for training climate emulators if you want to do machine learning based emulation. It's a necessary, and I don't know about necessary, but it's certainly a highly desirable component. There's quite a lot to potentially contribute to NEMO, particularly in the parameter inference stage. So I think the parameter constraint is a very big problem. And in that sense, it's a low-hanging fruit. There's a lot of the parameterizations are in there already. So there is quite a lot of work to be done in actually refining or tuning those models, or at least having an automatic way, a data constraint way of tuning those models. There are various things which are important for machine learning-based parameterizations, which are relating to the tools, but I think Alexis is going to be talking about those, so I'm not going to say much more about it. So I think I'm basically done. I will leave this one as part of it. So this is a picture I get from my I'm exposing my cat, a picture of my cat to various machine learning models I teach as part of the course. Just for the people who say machine learning will work, just naively work. So here you can say it really does not work because this is fundamentally this is a hard problem. So this is an issue with doing our sample regression, and others have similar problems, but even worse, and it's even more subtle than those. So the problem is where it's even more subtle. So when it's making mistakes, you might not actually know it's making mistakes. So it's important in my opinion, it's important to constrain those. So I think I will finish here. So thanks for your time.
Thank you very much, Julien, for your overview and your viewpoint on machine learning for NEMO in general and for ED parameterizations. Maybe we'll have time for one question from the audience before moving to. Go ahead, Julien.
Hi, Julien, can you hear me? It's Julien on the other side of the channel.
Not very well.
No problem.
Hi, Julien. It's
Yes.
Julien online here from Paris. I was wondering whether you could comment on how you see as a NEMO AD parameterization working group co-lead, how you see like the intercomparison of the different AD parameterization and how they should live and live together in future versions of NEMO?
So I think to me, it's the testing. So I'm always very suspicious of things that I can't test. And one of the things, so this is not, it's kind of, I'm sidestepping your question a little bit. So I think there is currently no strong testing framework to definitively say this thing does better, this thing does not do better in a documented way. So we don't really have a testing framework. So I think one important thing is for the testing framework to happen. Going back to your question a little bit, how they play with each other is that requires some investigation. We don't really know because these are things are not orthogonal. Right? So if you do one thing, then it could end up affecting the other things in a mutually incompatible way. I would say I don't have it, and we need a good testing framework, and we don't really have that at the moment. So I think if as part of this program there is a introduction or some sort of testing framework, that would also be very useful for us to know, at least at the NEMO developers committee.
Thank you, Julien. So thank you very much. Now we'll go to the presentation by Hugo Freza.
So I was just talking about the different types of turbulent systems that we have in Earth system models, including what's happening in the Earth core. It's not directly related to climate, but still interesting. And so what we do with numerical simulation is that we use the Navier-Stokes equations. Most of the time, the Boussinesq approximation for the fluid, but you have also the magnetic field when you are looking at the Earth core. And so these equations are discretized on the grid. And if you want to reach a realistic parameter range, you would need a grid that is very, very fine. So what you have on the left. And so if we look at the spectra of this grid, so we see the different ranges. So on the left, you have the big structures, for example, big tornadoes. On the right, you have the smallest eddies. And so in practice, it's not realistic it's not possible to go to grids that are so fine that you can represent molecular diffusion, for example. And so what people do is that they use what they call the LES, large eddy simulation, where the initial equations are projected on a grid that is coarser. And so what happens in the equation is that you have the original dynamic on a coarse-grained grid, but you also have to solve for this subgrid term, so the subgrid forcing. And so the effect of this subgrid forcing is to take into account what's happening on the smallest scales that have been removed from the simulation. So that's the goal. The goal of subgrid parameterization is really to find a solution to this tool. And so this is an open problem in physics for a long time, starting from the work of Smagowinski many years ago. And recently, it has been an active field using machine learning again. So people have started generating data from high resolution simulation and learning the correction, the subgrid term, as a supervised problem. So that's something that is now done and has been presented just before by Julian, I think. And so if I have time, I want to talk about two things. One, how to learn the correction, but using an online approach very quickly with some examples and some specific results that will be interesting. And then talking about how we could use emulators to avoid the fact of having the need for a differentiable solver. Okay, so first. So the system that we took it's a toy system, so it's simpler than the full Navier-Stokes equations on the sphere, but it's the key approximation. It's a 2D model. In this case, we made some experiment with a single layer of this model, so it's only a flat. It's only at the surface. And so there is this term in blue that we have to close. The dynamics look like this on the top right. And the term that you want to predict with the neural network is basically the one that you have on the bottom right. And so there's many difficulties that could happen if you don't model this term correctly. So what we would like ideally is the one on the left. But what happens sometimes is that the model is adding too much energy at mode scale, and you will see in the spectra an accumulation of energy at the smaller scales, which results in instabilities on the vorticity field. And if the model is too diffusive, then you have the opposite, and the field is completely smoothed out. You don't have any small scales anymore. So we just want a good balance between the two. So in turbulence, we have two ways of evaluating a model. That's the a priori, that we call a priori metric, where we just evaluate, for example, the mean square error or the correlation of the field that we predicted versus the ground truth. So this corresponds exactly to what you're doing when you're doing supervised learning. Basically, you're trying to fit the term. And we also have the a posteriori metric, where what we look is more the temporal evolution of the system that has been augmented with the subgrid model. And so in this case, we include the temporal aspect into the evaluation. And that was the motivation for what we call now online learning or a posteriori learning, or there's many names for this. So the idea is that instead of just trying to learn correction, we start from a reference state, so omega t0. And so we have the filtered one in blue. And if we integrate in time those two models, they start to diverge. And so we are able to compute a loss function between the entire trajectory and not only on the next substep that's represented by the subgrid term. And so what we do with online learning is that we minimize the error, but on the entire trajectory, not only on the next time step. So that was the idea. And in practice, it works quite well. I don't think I have so I don't have the animation, but what you see is that the reference DNS on the left, filtered DNS on the left, is very close to the one that's trained with the a posteriori method. The a priori, so using only unsupervised learning on the subgrid term, is not stable, so it's diverging very quickly. And so this is a model that's it's a classical model that's not using machine learning, but this model is known to be a little bit too diffusive, even though it's very stable over time. Okay, and so now, so it's an example from a different field, but I think it translates also in climate science. So in this model, we're looking at planetary interiors. So it's the interior of the Earth, and so you have a fluid that's also in movement. So basically, the equations are the same, but the domain is spherical, and also you have rigid boundaries at the outer and inner of the core. So this is an example from a code by people at IPGP. And what we did is that we tried to apply the same approach on this code. So we implemented a new differentiable code that is also spectral. So it's a spectral code in the azimuthal, but also in the radial direction. And so there was the first problem, is that when we filter the original field, the high resolution field, we have some problems because the grid in the radial direction is not uniform. So when you apply a spectral filter, you have some additional error that they call commuting error that you have to take into account. So what that means is that if you filter this equation and you compute the subgrid field like we did on the QG model, then it doesn't exactly correspond to the subgrid field, and learning a correction based on this would lead on accumulation of error, and so basically it doesn't work. And what it says is that it's very hard, if not impossible, to build an a priori training target. So we can't do a priori training. But there's no problem for a posteriori learning because we're not computing the subgrid term directly. We are only computing the fields that are filtered. Okay, so I mean this is more of this is very specific to the problem, but so in this configuration we have rigid boundaries. So this is not periodic on the radial direction, and so to take that into account properly, we have to transfer to a different basis. I don't know, in the atmosphere they use spectral code also. Maybe this can be of interest, but certainly not for the ocean. Okay, so it's the technical detail. Just a few examples of different configurations. So this is in what they call an exponential container. So dynamics that it gives is that you have jets, alternating jets, and so if you look at a radial profile of velocity, you have to see these alternating jets. And so in blue, this is the model that we trained, and this is very close to the reference DNS. In orange, this is this is the best thing that they have, which is hyperviscosity. So it's not really good. And we also see here that we are better on the potential vorticity. So this is nice. But the most interesting thing is that if you look at so it's a spherical container, it's closer to what we have in the Earth. And so in this case, the jets are smaller and smaller when you go to the outer boundaries, and you have actually Rossby waves at the outer boundary. And so this is very interesting because when we did the learning was only done on 1 turnover time, so it corresponds to like 1 centimeter. It's very small compared to the horizon of simulations that I show here. But only training using a very small temporal interval, we are able to learn the drift of the jets. So this thing that you see that's quasi-periodic, we're able to reproduce it, even though it was not seen in the training data. So this is very interesting. I think we have some similar dynamics in the ocean that we would like to reproduce. And I mean, we know that it can be possible with this kind of training strategy. Okay, take just a bit of details. So to have this, I mean, to make this possible, we need to do a gradient descent to learn our model. And if you're doing the a posteriori approach, you have basically you need to differentiate through the solver, and this quantity is often not available. For example, if you use a Fortran solver, you don't have access to the derivative of the solver automatically. And so people are using different kind of strategies to solve this problem. So you can estimate them using numerical derivatives, but that's not very stable. You can implement and maintain an adjoint of your solver, but that's time consuming. You can use automatic generation tools. So I don't know the status of that, but I think there's a few that are very interesting. And you can also implement your model using an auto differentiation language or library. So that's what we did, and that's what people are doing. For example, there's this DJ for Earth project in Julia, where they have implemented a differentiable ocean model and a differentiable atmosphere model also. And so there's a few different methods also to approximate the gradient. So using deep differentiable emulators or using different approximations. So there's a paper by List and paper by Said that do that. And so I don't want to go through this. Let's jump right there. So we wanted to explore a little bit the deep emulator approach, so where we emulate the small scale dynamics so that we can learn subgrid correction, but on using an online learning loss. And so just for illustration, we took a very small, very simple model, the Lorentz 96. So it's still chaotic. And you have two time scales. So you can have basically a term on the right that is coupled with the second equation. And so this term is, we can say that it's a subgrid term. And so what we want to do is to model this, but knowing that we don't have access to this quantity. So the idea is to, I mean, train an emulator, call it epsilon, that is close to the coarse resolution model. But with this model, so this simulator will be a neural network, and so you have access to the derivative of this model directly for free. And so this is basically the workflow. So if we look, we have in blue, it's the two time scales reference. And in orange, you have the one small scale. So the orange one doesn't have the coupling term. It doesn't have any subgrid term. And we can see, for example, I mean, here, we can see that it's slightly drift over time. And what we do is that we restart it. So we put it back on the reference every 30 time steps. And we train an emulator that is able to reproduce the dynamics of this system, so of the system that's not corrected by the subgrid term. And so this emulator will basically emulate the dynamics of the coarse grain solver. And so now, using this emulator, we can train on that a subgrid correction that we can then use, but using the real simulator that's not differentiable, because at inference we don't need the differentiability anymore. And so we did that. So on the Lorentz, it works very well, but the problem is also very simple. On the QG problem, it's more difficult. So if we look at, so this is the reference in the top left, that in bottom left, that's what happened. Well, that's what happens if you don't have any correction. And then we have different models. So on the most right, you have the model that's trained with the differentiable solver. It's the ideal case where you implemented your dynamics. And And so there's what I call the state loss, where the loss is on the state of the system, so vorticity, for example. And there's the subgrid loss, where the loss is basically on the subgrid term, but also online, so average over time, the trajectory. And so there's now two emulators. So there's a small emulator that I call SM and a large emulator LG. And so what we can see is that if we train the emulators on the state loss, there's always some instabilities that develops, and also some accumulation of energy at large scale. And so these two are not very convincing. However, if you train on the subgrid loss, but having a sufficiently good emulator, so sufficiently close to the reference, we're able to train, so this is this box, we're able to train something that's quite close to the reference, even though even if it's not as close as training a model using a differentiable solver. Okay, so maybe one thing just to illustrate what's happening, but also we don't understand what's happening. So we have some input that would be nice. So this what we're looking at is the error on the gradient of the loss based on the emulator versus the differentiable solver. And so when we are using the state loss, you can see that the loss on the gradient, the error on the gradient that you make on the gradient is very large. So you can suspect that this is why you are training a model, subgrid model that's not very, very good. But if you look at the subgrid loss, the error on the gradient of the subgrid loss, then it's much smaller. So we don't really know what's happening here, but yeah. And one thing that would be interesting would be to compare this approach using emulators to the different approximation methods that you developed, Said, and also the method by list, just to see how they compare, if this is really needed, or if you can use an approximation without having to learn an emulator. So that's something that we would like to explore. And I don't know the time.
I think you are fine.
Fine,
Okay.
30 minutes?
Yes.
Okay, perfect. So if you have any questions or things you want to discuss.
Thank you, Hugo. So a question from the audience? Go ahead.
I think Julian Mac mentioned this is being slightly not at ease with the fact that ML-based parameterization not followed some of the conservation laws and things we really care about when building realistic solvers. And he pointed out this idea that you could also imagine using online learning with a symbolic regression. Have you put some thought on this? You could help me?
No, I mean, I also think that it can be interesting. Just seeing if you learn something that's different using online learning than using offline learning, that would be a finding. So I would be very curious to see. I thought that some people already tried this, but apparently not. So yeah, that's something that we should try, since we already have everything set up. Yeah. Yes.
When you train them, do you train on simulator prediction?
No, it's also trained on 25 time steps, so the same thing that we do for the subgrid term. So it's
how do you separate the errors you accumulate from the parameterization? Like the errors for so you parameterize tomorrow.
So in 25 time step, the model has not enough time to go crazy. So it's still stable after 25 time steps. But if we go beyond that, yes, that would be a problem. That yes.
I have a very late question. Did you did you think about trying on different states and how it adjusts to different background states?
You mean trying on the velocity, for example,
Yes.
instead of the vorticity?
Yeah.
Yes. We did that actually. For the QG, we always did it on the vorticity, and this is where we've seen the best results. But for this problem, the loss is actually the kinetic energy, so integrated using spherical coordinates. So it's in this case, it's on the velocity that we had the best results, because our loss is always a mean squared error. So for the QG model, for example, it's a non-strophy, so it's vorticity squared. And in this case, the velocity was the best field. I don't have any specific rules or explanations about this, but it's problem dependent, I believe.
And what about so you tried for different parameters of the rotating?
It's different geometries, but we also have a configuration with a different. I mean, we have in the spherical geometry, we also have an example with a configuration that's more turbulent, and it works also very nicely.
So if there are no other questions, thank you again, Hugo, for your presentation. Now we'll be moving to the last presentation of this session, who is by Alexis, who is going to talk to us about the Nemo Python wrapper.
Okay, so I'm Alexis. So I work at EG in Grenoble, mainly on the development of interfaces between ocean models and machine learning components, and in a more general way, Python procedures. And in this scope, I will today present you with a demonstration project that I'm working on. So a Python wrapper for the Ocean General Circulation Model NEMO. So some of you in the audience have already assisted to this presentation, so you can play the game of how I don't think I do it between now and the last time. Well, so the starting point of this work is that we have so the ocean model NEMO that is written in Fortran. Which is a choice made because Fortran is optimized for high performance computing, which is necessary for this kind of operation and modeling. And what is done in practice is that once NEMO is compiled and parameterized with the input files, the simulation starts, and we need to end to this one to finish. And what we want to achieve now is to split up the NEMO main routine to steer the steps of the ocean modeling experiments. So just to be a bit technical here, the idea is to keep the NEMO function written in Fortran and to split up them in separate parts. And for now, the NEMO main routines that have been split up is the initialization phase, time iteration, finish phase, and the possibility to get a copy of the internal state of NEMO toward the Python memory and to import fields from another process from the Python memory toward the NEMO to the NEMO memory. And the idea is to expose those functions to the C language and to wrap it into the Python with a Cython layer to be available from the Python language. And all over it, I just designed a Python interface that is here to provide a user-friendly interface to use those splitted up NEMO routines with some information about the NEMO internal state. So no heavy operation is performed by Python, it just provides some information about NEMO. And the Python wrapper just send instruction to execute those parts, those speeded up NeMo parts. So the Python wrapper is named Aronnax. It's a character from the Jules Verne's novel 20,000 Leagues Under the Sea. And I tried to design it in a way to not get lost usual NeMo users. So for the deployment, NeMo is compiled as usual as an executable, so nothing changed at this moment. And the Python wrapper then just need to be installed, and it will just pick what it requires. So from the already compiled NeMo sources and the additional sources to deploy the Python wrapper, and it can be seen as just a plugin instead of something that replaces NeMo. And so for the moment, the development prototype is the global circulation configuration Orca1. And I will give you now just a bit details about the execution thread, because I noticed that the confusion is oftenly made between a NeMo job submitter that Aronnax is not. So Aronnax starts a job and starts instances of NeMo within its own job, and it doesn't start other jobs for NeMo. This kind of tool already exists. It is developed by the Methods, and so this is really different here. So you can start several NeMo within the same running job. So now let's go for the demonstration. Zoom a bit. So for those who are not familiar with NeMo, so we have a copy of NeMo just right here. And and I'm here in the experiment directory of the Orca. So it's here on Orca2, but it works the same with Orca1. And if we just take a look in the experience and running directory, what we have are the usual files required to run NeMo. So the name list to parameterize the model, the XML files for the input IO, so the input output server, and several files required to force the simulation. And to spare time, I already compiled NeMo here. So the executable is here. And what we would do usually is to copy the executable to the running directory, execute the simulation, wait until it ends, and then do whatever we want with the results. So here in the running directory, so I did not copy the NeMo executable because we will run it directly from the Python wrapper. So for the moment, nothing is new. This is the classical way of deploying NeMo. And what would be new now will be to so clone a copy of Aronnax. So the GitHub repository is not public yet, so I already cloned it in my laptop. And what we just need to do is to install it with just the famous command pip install. It won't take that long. Okay, should I run the command instead of speaking? I have said that last time. Well, anyway, I can start. So for the demonstration, I will run a notebook. Because it's notebook, it's executed sequentially, but it's completely possible to execute the Python wrapper on several processes. So the Python wrapper will automatically configure NeMo and the MPI decomposition to execute NeMo. Oops. So if I go in the experiment directory, run, and yep, worked. So here we are. So we start by importing the Python wrapper Aronnax and not Aronnax. better. And then we can start in an instance of NEMO, so from the package. And I give it a name. So let's say Biorca2. So now NEMO is starting up. And I can print the current state of NEMO. So we have here the instance of NEMO with its name Biorca2. Current iteration is 1 and simulation time 0 because it just started. And we have just a quick test to check if NEMO is initialized. So this is just to avoid to initialize, to start another instance of NEMO if first one is already running, because it means that we would go again in the initialization routine of NEMO, which could lead to unpredictable behavior except crashing. And if I go back in the execution directory, so we can see, so we cannot see, but trust me, a difference between the last time I went in this directory. So new files, so ocean outputs, timing output, which are classical NEMO logs that are created when NEMO starts. So NEMO have created them, so not from the standard way of executing NEMO, just because I asked it to start from the Python wrapper. And if I check the content of the NEMO log, we have the initialization messages, and now NEMO is in an awaiting state. So waiting for instruction coming from the Python layer. And the last log of NEMO is the TRD init, which is the last initialization routines that has been performed. And now we can send NEMO some instructions. So we will start by asking it to advance in time by 10 iteration. So the time step is fixed. So it is specified from the name list. And at the beginning, I wished to impose it directly from the Python wrapper, but I'm not sure how NEMO will respond if the time step change during the same execution. So we have now some information about the NEMO state. So time advancement has reached iteration 11, so ready to start the computation of iteration 11, and simulation time is 0 because it's still a prototype and some features are missing. And if I check the content of the NEMO log, we can see that this one has been updated with the classical logs that NEMO writes when it's running. And we can also check the content of the time step file. That is a file that NEMO updates every time an iteration is performed. And we can see here that NEMO performed 10 iterations, and this is great because this is what we asked it to do. So now we will see the get functions, and we can copy the fields of NEMO from the very Fortran core memory toward the Python core memory. So with this get function. Okay, so now we have the temperature and salinity field. So here, 1 minute to go, maybe technical details to explain how the key T and the key S correspond to the temperature of salinity fields. So because we need to do this association, so if I go back to my slide up, there is a source file that can be modified by the user, and I try to design it to be as intuitive as possible, in which just this file can be modified with this small field function. That is a Fortran-like dictionary in which the association between a name, the key, so for example, U, is associated with the array UU that corresponds to the velocity in NEMO. And so because depending on what the user wants to do, I cannot anticipate all the fields that can be that could be used in the future. So this is the solution I tried to design to make it user-defined and user-intuitive. And if this file is modified, we just need to re-pip install the package as I showed you earlier.
I have a quick question,
Yep.
Alexis. What is GP-tem and GP-sol?
So this is so TS is the array in NEMO that contains the temperature and the salinity field. So don't ask me why it has this design.
Okay.
And GP-tem is just here to make the difference between the two. And yeah. Okay. So here we have copied the temperature and salinity fields from NEMO into the Python memory, and we can perform some operation on them. Anything you want. So here I just compute the mean of the surface temperature. So we have 7 degrees, which is not aberrant. Now we can start, we can still advance, we can create another time advancement segment. So just to showcase that we can separate, you can perform different time advancement segments. So for the moment, I just specified number of time steps, but I wish to make it evolve to impose a specific duration, for example, advance 1 day, 1 month, and so on. And now we will see another feature of the wrapper, the possibility to impose a field coming from Python to NEMO. So with the function not get but set. So here again, we specify the keys that corresponds to the field we want to impose. And here we will impose the temperature field we got at iteration 10 multiplied by 2. And we impose it at iteration 16. So for the moment, nothing happened, just NEMO has been updated. And just to showcase that the update has been well performed, I asked NEMO to advance by 5 time steps, and simulation failed as expected because we have imposed non-physical field. So it worked. Well, it failed, but it worked. And if we check the NEMO output log, so we can see the error message corresponding to a diverging to a diverging physical state. And we can also check that NEMO is not running anymore. So we can start another instance of NEMO if we wish to. Last slide, so to summarize what could be performed with this tool. So the first category would be to integrate NEMO in higher level workflows, like for hybrid modeling or data generator for training. It can also be compared with recent models that propose this kind of interface, like Ocean Elegance or Veros. Another possibility is to improve the user experience. It can be used as teaching material. Of course, it provides a more modern interface. And one colleague in Grenoble suggests that it could be used for debugging to bring NEMO to the very end, to the very step before the crashing, and start to investigate where the error could be. And so currently, so the wrapper, it's at early development stage, and we wish to add some features to create automated restarts and to modify the namelist parameter just to offer the user the possibility to do everything directly from the Python interface. And so the GitHub repository is not public yet because I still need to find a license. And, so I need to take the time to find a license. And yeah, that's it.
Okay. Thank you very much, Alexis. Do we have questions? Yeah. Okay.
So I teach, but I teach using the LMDZ, and I think it would be very useful indeed to show the students how the models advance and take one step and another step. without waiting for the full model to run for a long time. So my question would be, how easy is it to adapt to the model?
So yeah, the development is NEMO specific, of course. I don't know LMDZ, so I wouldn't say it's difficult to extend the approach to the model, but the work will be specific to the model for which you want to create the wrapper. So yeah, I don't really know. Yeah. And of course, so for the moment, I split up the NEMO routines between initialization, time step, and finish. If we would wish to call smaller parts of NEMO, so for the moment, I still don't know how we could do that, but it requires to think in advance about designing the way of calling different part of NEMO. So I just do this precision because it's kind of related to this.
For now, it calls the full model and
yeah, for example, if you want to get so the temperature or something, a field from NEMO, it can be done at the end of time step. So a field that is created during the time step, but not kept at the end, is lost, of course. So
you cannot go to just execute this routine.
Yeah, not no yet. Yes, hope. We'll see.
Go ahead then.
I was just wondering whether one of you could explain how this new functionality would be critical for the LEAP-HCS project, in particular when it comes to implementing advanced workflows like EGA.
Do you want to try to answer? Or?
Oh.
The thing is that when we, so at least when we want to do online learning on models that are not differentiable, typically NEMO, there are lots of different problems. And one of them is actually the fact that, as I said in the presentation, we need to interface the Python and the things that we can differentiate with things like NEMO that run on Fortran and that we cannot differentiate. So I think that these tools actually do exactly that, in the sense that now when I develop, for example, gradient approximation in order to solve this online learning problem, I can see NEMO just as a black box inside of my optimization problem. So it's just, it's a model that I can run forward. I cannot differentiate it, but I'm here to develop methods that can still solve the optimization problem without having to differentiate NEMO and without having to think about how to interface NEMO with Python, which is kind of a big problem, at least from my point of view. Maybe what I would like to see, and then I will return the question to you now, is so when you said in the perspective that you are trying to implement an automated restart, so can you specify what you mean about that? Or?
Yeah, so for the moment, I can start NEMO, make it run till specified time step, and then finish NEMO. But I cannot specify to start. I cannot start another instance from the last run. So I could, but I need to go back in the name list and so the old way. And here the idea would be I can run NEMO once, finish it, starts again, and specify to restart on the previous run directly from the Python interface. And
but if I understand correctly, and with this tool, we can, for example, specify things like temperature, salinity fields, velocities from a netcd.
Yep.
So we can restart NEMO from.
Yeah, just that I didn't try it yet, and the devil is in the details.
Yeah, sure. But
But
So to me, in order,
yeah,
maybe just to continue with your comment, to me, what I still need in order to do things like online learning on Nemo with this tool is maybe validating a restart of the Nemo from some kind of an external field, let's say netcdf, things like that. So this is thing number one, and as I understand, it's close to being validated. Maybe the second thing is I finish this. The second thing is, can we, for example, turn on and off parameterizations inside the OCA configuration? Because this is critical.
So you mean during the execution of Nemo?
Yeah. So for example, in the instantiation of the configuration, can I, maybe in the name list, can I like add a flag and say like deactivate the AD parameterization?
So on the paper, yes, you can. But I don't know how Nemo will respond if you do this while Nemo is running. So, or another possibility to do would be, okay, I want to change this parameterization. So we force the termination of Nemo, adapt the name list automatically, and it then starts another instance of Nemo. And at this moment, the automatic restart will be useful. And at this moment, yeah, it would be like if you have changed the parameters during the run.
No, I think what I need is actually simpler than that, but we can discuss further about it.
I'm more technical.
I think what I mean is a little bit simpler than that. I don't know if it answers your comment, Julien. Any other questions for Alexis?
Just a suggestion, if we were looking for advice for a license.
Yes.
That's you could contact invest core project, because that's their job.
Okay.
And distribute codes and data.
Okay, and also because the question is also related because it's close to Nemo, so I don't know how far. Okay, cool. Thanks for the advice.
Okay, so if we don't have any other questions for Alexis, thank you again for your presentation. So this ends up the first session of this kickoff meeting. So thank you to all of you who are present here, either online or in person.